Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be working through the June 2012 Unit 1, Paper 2. We will be working through question 2, which was a question on solubility product. So the question says, describe using 5 essential steps an experiment which can be used to determine the solubility product of calcium hydroxide at room temperature. So whenever we need to do a solubility product determination, there are 5 key steps, and here they are. So the first one is that we have to make a saturated solution of calcium hydroxide by adding enough of the solid to a known volume of water. Then we're going to shake that mixture and leave it for 24 hours to allow it to reach equilibrium. After it reaches equilibrium, we're going to come back and we're going to filter off any solid calcium hydroxide that wasn't a part of that equilibrium, right? So we'll just filter that off. And once we filter that off, we're going to titrate samples of the calcium hydroxide solution with hydrochloric acid of known concentration, right? And the reason why we're doing that titration is to be able to calculate the concentration then of calcium hydroxide solution from those titration results. And once we have the concentration of calcium hydroxide, then what do we have? We automatically have the concentration of the calcium 2+ ions, as well as the concentration of the hydroxide ions. And so what we're going to do is we're going to plug those concentration values, right, in this expression here in order to be able to calculate the KSP, okay? Because this is the KSP expression for calcium hydroxide. So if we know these concentrations and these concentrations from our titration results, then we can find the KSP, okay? Which is the solubility product of calcium hydroxide at room temperature, okay? All right, so let's keep it moving. We're going to move on to part B. Part B says the solubility product, or the KSP, at 25 degrees C for calcium carbonate, CaCO3, was found to be 5.0 times 10 to the minus 9 moles squared, dm to the minus 6. Define the term solubility product. So the solubility product is the product of the concentrations of each ion in a saturated solution of sparingly soluble salt at 298 Kelvin raised to the power of their relative concentration. So very much as how we just did the setup for how we would have found the KSP of calcium hydroxide, that's exactly how we would write it, and that's how we define it, right? It's just a product of ion concentrations in that saturated solution at that temperature, okay? So now we're gonna write the equation for the dissociation of calcium carbonate. So in any KSP problem, this will always be our starting point, is to write the equation for the dissociation of whatever salt we're studying. So in this case, we're studying calcium carbonate. So here's our equation. We're gonna start out with calcium carbonate in the solid phase. We're gonna add that to water so it gets dissociated, so those ions get separated, and we end up with the Ca2+ ion in the aqueous phase, and we have the carbonate compound ion in the aqueous phase as well. Okay, so that's how calcium carbonate dissociates in solution. Okay, now we're gonna write the expression for the solubility constant for calcium carbonate, right? And so what we do, we're always going to start from our balance equation, which we just wrote, right? Our equation. And we look at our equation and we're looking at our product side, right? And we're going to do the concentration of these ions times each other, right? And because it's 1 to 1 to 1 mole ratio, we don't need to raise any of them to any powers, okay? So my KSP expression for calcium carbonate will just be the concentration of Ca2+ ions times the concentration of the carbonate ions, okay? And that's my KSP expression there. Okay, so now we're being asked to calculate the solubility of calcium carbonate in pure water. So a quick point I want to make here about the use of the word solubility. So the solubility, when we're doing solubility product, the solubility can be used interchangeably with concentration, okay? And it has the same units as concentration. So we have the same units of mole per dm cube, since that's the units of concentration, okay? So just keep that in mind, that can be used, you know, interchangeably with concentration. And as a result of that, it would have the same units that concentration would have. So we expect our final answer whenever we're finding the solubility of a particular compound to have units of mole per dm cube. Okay, so just keep that in mind whenever you're finding solubilities. So we're asked to calculate the solubility of calcium carbonate in pure water. So that is our solvent. It's only gonna be that we're dumping the calcium carbonate in water and seeing, creating a saturated solution there, okay? So here's our calculation. Again, we're gonna start with our equation that we had written earlier. And then after that, we have our KSP expression, which we wrote earlier as well. So now is where we have to make some simplifications, right? And so as I said earlier, because from the balanced equation, we know that 1 mole of the calcium carbonate dissociates to give 1 mole of calcium 2+ ions and 1 mole of carbonate ions. That because we know that any amount of concentration of calcium carbonate I started with, that's exactly what I'll get in calcium ions, and that's exactly what I'll get in carbonate ions. And so we can simplify this expression by saying, okay, because it's a 1-to-1-to-1, I know that my calcium ion concentration will be exactly the same as my carbonate concentration. So those two things are equal. And so if they're equal, when I come back up to my KSP calculation, I can legitimately just plug in wherever I see calcium ions, I can also, you know, just like put the carbonate, they're the same. So they're the same thing, so I end up squaring it. So it ends up being KSP is equal to calcium ion concentration squared, because if these two are the same and I do Ca2 plus, right, times Ca2 plus, because that's what the carbonate is, it's the same, then that's essentially just Ca2 plus squared. So that's my simplification there. And when I do that simplification, I get this for my KSP. Then if I want to find the concentration of the calcium ions, which is effectively the solubility of calcium carbonate, right? So let's just jot that there real quick. My concentration of Ca2 plus ions is effectively my solubility of calcium carbonate, because whatever that number is, right, is determined by how soluble the calcium carbonate is. So my Ca2 plus ions now, I'm gonna square root the KSP in order to find that, to isolate for that. And when I do that, I'm gonna square root this number here. And when I square root that number, I end up getting 7.1 times 10 to the negative 5 units of concentration, mole per dm cube. So that is my solubility of calcium carbonate when it's in pure water. Okay? So that's what we get there. And so we're going to move on now to the other part of this question, right? And the other part says, calculate the solubility of calcium carbonate in 0.1 mole per dm cube of sodium bicarbonate, so Na2CO3. Okay, so what's different here is what we're gonna have to really zoom in on. What's different from when we were finding it in pure water? We're no longer in pure water now. You know, the calcium carbonate is being dumped into what? Na2CO3 solution. So here's the setup. The setup is the same for the calcium carbonate as before, where we have it dissociating that way. KSP expression is the same. However, what we will notice now is that the calcium ion concentration will not be equal to the carbonate concentration anymore. Why? Because we have carbonates coming in from the sodium carbonate solution, right? And so those two things are not going to be equal anymore, despite this ratio that we knew existed when it was in pure water, right? And so effectively then what we're going to do is the solubility or the concentration of calcium that we had from before, right? That was 7.1. Let's go back real quick and see what that number was. See what that number was. That was 7.1 times 10 to the minus 5. So we're just going to keep that number handy. And so when it was just in pure water, right, my Ca2 plus concentration, so in pure H2O, right, my Ca2 plus concentration was equal to 7.1 times 10 to the negative 5 mole per dm to the minus 3. And that was also what my carbonate concentration was, because remember they were equal, right? So anything one was, the other was the exact same thing. So that's what my carbonate concentration was when I was in pure water. But now that I'm in sodium bicarbonate, there are going to be carbonates that are coming from the solution. So now my carbonate concentration will effectively be that of the, so whatever was in the sodium carbonate solution. Because when we compare this concentration to the concentration of carbonates that would have been present just from the water, we see that this number is far bigger, much bigger than that number. So this is going to be now the concentration of carbonate ions that we use. And so now the calcium ion concentration is going to be our unknown. Because remember, as we said before, we can't equate them anymore. We have to use the carbonate concentration that's coming from this solution. And so now what remains then is we have to find what the new carbonate, the new calcium ion concentration will be. And so to do that, we again go back to our KSP expression. It said KSP is equal to the concentration of my calcium ions times the concentration of my carbonate ions. So therefore now, if I want to find, right, I now want to find this, then I have to rearrange my KSP expression, making the calcium ions a subject. And when I do that, I'm going to end up dividing my KSP by my carbonate concentration, okay? And when I do that, I'm going to come up with a number of 5.0 times 10 to the minus 8 mole per dm cube, okay? So let's just collect everything now. So for the pure water, right? So in the first instance, for my pure water, this was my solubility of calcium carbonate, right? Now, for when I did in the 0.1 mole, right? So this particular instant that we just calculated, in my 0.1 mole of sodium bicarbonate, I found that the solubility of calcium carbonate now ended up being this. So it ended up being now 5.0 times 10 to the negative 8 mole per dm cube. So what do we notice right away? Right away, look at this. This is on the order of 10 to the minus 5, and this is now on the order of 10 to the minus 8. So do you see what happened? The solubility, right, of our calcium carbonate decreased when we place it in a sodium bicarbonate solution. The solubility decreased. We have a smaller number in this instant, right? So just keep that in mind. The number is now smaller than what it was before. The solubility has decreased significantly. Okay, so let's move on to the other question. Right? The question says, what is responsible for the difference between the solubilities in C part 1 and C part 2 above? And the phenomenon that is known as the common ion effect is responsible for the difference in solubility seen. So this is what explains the decrease in solubility of calcium carbonate that is seen when it was added to the solution of 0.1 mole per dm cube of sodium bicarbonate. So because we have ions in common now, we have the carbonate from this guy and the carbonate from this guy, it decreased the solubility, okay? And you know, just for a little extra here, let's go back to the equilibrium expression and just explain what happened there in terms of the decrease in terms of Le Chatelier's principle. So let's look at this expression here, right? Let's look at this equation rather, right? What's happening? So this represented my calcium carbonate in pure water, right? So there's an equilibrium that's established there. If I take this calcium carbonate and I put it in a solution where there's more there's more carbonate ions in there, then effectively what am I doing? I'm effectively increasing the amount of this. And so based on Le Chatelier's principle, the equilibrium would have to shift to the left, right? The equilibrium would have to shift to the left in order to use up the excess carbonate that disturbed my equilibrium. And so shifting to the left is gonna what? Precipitate out more calcium carbonate. And so that's exactly what we see. So our decrease in solubility can be directly tied to the precipitation of more calcium carbonate, okay? So all of that comes full circle with this explanation or this phenomenon of the common ion effect that we ended with here, okay? So again, common ion effect is going to decrease the solubility of our compound. If there's an ion in common with it, in the solution, it's going to decrease the solubility. And that decrease in solubility is directly linked to there being no more precipitation of the solid form of what our salt was. Okay? And so with that, we've come to the end of this video. Definitely give it a like. Consider subscribing to the channel. Share this video with a friend or a classmate. And we will see you in our next video.